Hi all, in section 1.7 we're talking about combinations and compositions of functions. Combinations is pretty easy, it's just addition, subtraction, multiplication, and division. Before we get into either one of those concepts though, the first thing and probably the first 10 or so homework problems will just have you trying to make sure you can understand how to find the domain of a function. So what values of x does the function exist for? Combine functions using the algebra of functions specifying domains, form composite functions, and then determine the domains for composite functions. That can be a little tricky sometimes. And then write functions as compositions. All right, so now, first up, if I'm trying to find a function's domain, what's the key thing? Well, you need to find the restricted values. And whenever we're talking about restricted values, values that cannot be in the domain, this last sentence here is the extremely important thing. Exclude from a function's domain real numbers that cause division by zero. So if you have a rational function or any fraction with variables in the denominator, they can't equal zero or else the fraction is undefined. And any real number that result in an even root like a square root, having a negative number on the inside of it. So I say even root there because it's not just a square root. It could also be a 4th root, a 6th root, an 8th root, a 58th root, whatever even root. It cannot have a negative number on the inside of it. Now keep in mind, if you have an odd root in your problem like a cube root, you don't have to worry about the numbers inside of it because it's going to exist for any value of x on the inside. Now, let's go ahead and look at a pretty straightforward rational function here. If I ask you to find the domain of g of x is equal to 5x over x squared minus 49, the first thing I want to point out, and it's probably one of my pet peeves, I will see students that say, "Oh, x cannot equal 0 because the numerator cannot equal 0. Why? You can have a 0 in the numerator. 0 divided by any number is going to be 0. But what I can't have is a 0 in the denominator. So anytime you have a rational function, all you ever have to do to find the restricted values and set up the domain is say that denominator cannot equal 0. Please remember, numerator is fine. So I can say because the division of 0 is undefined, we must exclude from the domain the values of x that cause the denominator to equal 0. I set the denominator equal to 0, find those values. Gives me x squared is equal to 49. I take the square root, positive negative square root of 49 gives me x is equal to positive or negative 7, causes that denominator to equal 0. So that means we need to exclude the values of 7 and negative 7 from the domain of g. So then finally I would say, well, tell me what the domain of g is in interval notation. And you would say, well, g, I think it's any value except negative 7 and 7. How do I say that? Any number from negative infinity to negative 7, union, any value from negative 7 to 7, union, any value from 7 to infinity. Up next, if we talk about this is the combinations of functions where we have addition, subtraction, multiplication, and division. The things I'm wanting you to understand on this page is that whenever we have the notation f plus g of x, it just means you're going to add f of x plus you're going to add g of x. If you have the function f minus g of x, it's f of x minus g of x. Fg of x means f of x times g of x. And if you have a quotient here, you'd say, well, it's f over g of x. That's going to be f of x over g of x. And of course, that's going to create a rational function where you're going to have the further restriction, g of x can't equal 0, or that fraction does not exist. Now, in terms of the domains of any of these combined functions, you just have to look for the intersection of the domains of f and g. It has to be numbers that both make f work and g work to make any combination of f and g work. Now, let's look at that in the following problem. Now, I don't have to worry about the domain of this problem because notice both f of x and g of x are polynomials. The domain for any polynomial is all real numbers So the domain of any combination of these two is automatically going to be all real numbers, negative infinity to infinity. For the first notation, I said, well, let's show f plus g of x. You said, well, that's your f of x function plus your g of x function. So I take x minus 5, I add it to x squared minus 1, and when I write that in descending order, I get x squared plus x, and then I would have minus 6. So the domain of f plus g is what I was talking about. It's the intersection of the domains of both of these groups. Both of these groups have a domain from negative infinity to infinity, so their combination also has that. And you can see that's what I put right here. Now, if I talk about composition of functions, that's where you've probably in lower level classes called it fog and goth. But I would rather you say f composed with g or g composed with f. Or you could even read it as f of g. That would be okay. The composition of f with g is denoted as f composed with g and is defined by the equation f composed with g of x means it's f of g of x, meaning g of x is going to take the place of x within f of x. And now keep in mind, it's always the second one that's taking the place of x into the first function. So now, if I want to look at the domain of a composite function, what I need to think about, and this right here helps out. I know that the domain, in order for it to exist, I know that the inside function must exist. I can't evaluate f of g of x if g of x doesn't exist. So that's why I say x must be in the domain of g. Now notice I don't say x must be in the domain of f, but what happens is whenever you plug g of x into f, g of x cannot be a value that's going to cause f of x to not exist. So I have to say g of x must be in the domain of f, and we'll show what that looks like here in just a minute. First of all, let's look at a pretty straightforward one here. If I'm asking you to forming the composite function here, I have a linear function and a quadratic, both have a domain of negative infinity to infinity. So their composition will also have a domain of negative infinity to infinity. I'm going to say f composed with g is the same thing as f of g of x, which means I'm going to take the function g of x, put it into the place of x within f of x. So I have 5 times that quadratic, and then plus 6. I distribute the 5 through, of course. I'll get 10x squared minus 5x minus 5. I already had the plus 6 right there. Combine the minus 5 and plus 6 to get my 10x to the second minus 5x plus 1. Now, when I was talking about finding values of the domain of f of g of x, the values must be excluded, the following values must be excluded from x. So they're not going to be part of the domain. If x is not in the domain of g, it cannot be in the domain of f composed with g. This is essentially what I was saying 2 pages back. X has to be in the domain of g. And then any x value for which g of x is not in the domain of f must not be in the domain of f composed with g. All right. This problem will make that second one make more sense. So first of all, let me point out, if I just said, hey guys, what are the restricted values of f of x and g of x? Well, you could easily see you're going to have a restricted value of 0, and you would have a restricted value of -2. So if I just ask that, that would be the restricted value, -2 and 0. And if I did any combination, f plus g, f minus g, f times g, f over, I would still have those same 2 restrictions. However, if I'm doing a composition, f composed with g, yes, I do have the domain restriction of g of x, but no, I do not have the domain restriction of f of x. Why? Because you never have f of x in the problem. The problem is going to be f of g of x. So f of x never exists in this composition. G of x does exist. I have to evaluate the inside function, and then substitute that in the place of x within f of x. So I don't care if f of x was restricted at -2. I need to find out what f of g of x is restricted at. Okay, so let me go ahead and do the composition, then we'll talk more about the domain. If I say f composed with g of x, it means f of g of x. We're going to take g of x, substitute it in the place of x within f of x. So I have 4 over 1 over x plus 2. Now, what I went ahead and did is as I said, that fraction looks so much better if I get rid of the fractions within the fraction. So I get rid of the complex fraction by multiplying the numerator and denominator by x. That gives me a 4x in the numerator, and when I distribute the x to the denominator, it's going to give me 1 plus 2x. So here's my simplified expression for f of g of x. That would be my final answer for this composition. Now, let's talk about the domain restrictions of that. So when I'm thinking about the domain restrictions, I can say, well, I know I said it's f of g of x. So g of x was my inside function. F of g of x cannot exist if g of x does not exist. So I have to say, well, I can't have g of x not existing, so I do need a restriction. X cannot equal 0, or else I can't plug a g of x in. Now, once I do plug in the g of x, and I simplify out my f composed with g, think about what further domain restriction. So when you try to plug a g of x into the place of x, now this is my denominator. Well, again, I have a rational function. That denominator cannot equal 0. So over here, I've just said that 1 plus 2x cannot equal 0. So 1 cannot equal a -2x. -1 over 2 cannot equal x. That's what I've done right there. I set that denominator and said that denominator cannot equal 0. This would be the value that would cause it to equal 0. So now again, please note in this problem, x equals -2 is not, I repeat, not a restricted value in the composition, because f of x never existed in this problem. It was f of g of x. So I had to keep the domain restriction of g of x, and then I had to look at the domain restriction of the composed function. 1 plus 2x could not equal 0. It gives me this one. So I have two restricted values, 0 and a -1/2. So the domain of the composed function f of g of x would be from -∞ up to the lower restricted value, -1/2. Union the lower restricted value, -1/2, up to the higher one, 0. And then union the higher restricted value of 0 all the way on up to infinity. Now, if I give you a function such as h of x here, and I say, I want you to decompose that function. If I tell you that h of x is a composition of f composed with g, what you're supposed to be remembering here from, even in this problem that we just did right here, please notice when we said f of g, you say, okay, g of x is going to be a function that I have to put inside of the overall function f of x, which was 4 over x plus 2. So whenever you're trying to decompose, you need to be looking for an inside function and an outside function. Well, clearly here, I have an inside function of x squared plus 5. What is it inside of? Well, it's inside the function the square root of x. So if I had let f of x equal the square root of x and g of x equal the function x squared plus 5, please think f composed with g, you'd say, well, f composed with g. You're going to plug the function g of x into the place of x within f of x. You say, well, yeah, okay. Yeah, that's going to give me back the square root of x squared plus 5. Gorgeous. That's the decomposition of functions where you have to write them out in terms of f and g. Now, there's a bunch of homework problems, more so with the composition of functions, but there's a few at the end with the decomposition. Please make sure you understand those as well. All right, guys, that finishes out this section. Let me know if you have any questions. Please make sure you do look at my homework solutions. I think they'll help as you go through the My Math Lab assignment.